Welcome to EPG Pathshala lectures on numerical methods module 2. In this module, we will be learning on Neville's algorithm for finding out the Lagrange's interpolation, evaluating Lagrange interpolation polynomial, time complexity of the Lagrange interpolation algorithm and the error analysis. These are the three learning objectives we have set for this particular module. Now, it would be quite tedious to compute nth degree Lagrange interpolating polynomial for large values of n. You have seen that in the last module, when we were working on the example, we have taken only 4 data points, and that was deliberately done because these computations will become simple in that case. But if we take say 10 data points, then if you want to really evaluate the y value at any point using such a Lagrangian interpolating polynomial, then it will be very difficult, because every time you have to take the product of 10 factors in the numerator, then 10 factors in the denominator, and then divide, and so there will be several such steps there. There is an algorithm called Neville's algorithm, which can be used for systematically and efficiently evaluating the Lagrange interpolating polynomial, and that algorithm we are going to learn in this particular module. So, we are introducing the notation for that. So, for 0 less than to j less than to I, let q I j x denote a Lagrangian interpolating polynomial of degree j on j plus 1 nodes, which are given by x at I minus j, x I minus j plus 1 up to x j, x I up to x I. So, x q I j will look at data points which set of j plus 1 data points which ends at x I, starts at x I minus j. So, there will be totally j plus 1 data points, and over this j plus 1 data points we can get a Lagrange interpolating polynomial of degree j. So, that polynomial is denoted by q I j x. Note that q I 0 x, that means degree 0 means it should be constant, and that is given by y I, which is the observed value of the data at data points at x 0, x 1, x 2, x 3, x n. So, y I is nothing but observed value of data at x I. For all I equal to 0, 1, 2, 3 up to n. So, q I 0 x is given by y I for all I equal to 0, 1, 2, 3 up to n. q 1 1, q 2 1, q n 1 are all linear Lagrange polynomial over nodes x 0 x 1, x 1 x 2, x n minus 1 x n, because see the first suffix, second suffix gives you the degree. So, because in all this second suffix is 1, all these are linear polynomials, and first suffix gives you the last data point, last value of x I. So, that means for 1 it is x 1. So, previous value will be x 0. So, we will get 1 point previous to the given point here. So, x 1 x 2 like that we get x n minus 1 x n and so on and so forth. Thus, q n n, if you take q n n, then q n n will be a nth degree polynomial, nth degree Lagrange polynomial, which will be interpolating y I at the nodes, all nodes x I, because you have to start n nodes previous to that. So, x n n minus n, so that will be 0. So, x 0, x 1, x 2, x n. So, that is precisely what we want. So, q n n is the precisely the Lagrange interpolating polynomial over all the given data points, and that is what we want to compute. So, input. So, when you are writing this Neville's algorithm, the input to the algorithm what we have to give is the n, which gives you the number of data points, n plus 1 data points. So, that n we are considering as input. the degree of the polynomial that we want. The data points xi yi, the actual data points xi yi for I equal to 0, 1, 2, 3 up to n, and these data points we are taking it in such a way that they are distinct. In fact, basically they should be distinct. We are arranging them in the increasing order, which is not absolutely necessary. So, we can take it distinct data points and a point x at which you want to estimate value of y. So, that point should be within that interval x 0 x n, because we are writing it in the increasing order, x 0 will be first value, x n will be the last value. The algorithm is very simple, and what it says is there is a simple formula. In fact, we can prove this as a theorem that q I j will be given in terms of q I j minus 1 and q I minus 1 j minus 1 using this particular expression or formula there. So, what we are trying to do is we are initializing q I 0 as y I, because we already said that q I 0 will be equal to y I for all I equal to 0, 1, 2, 3 up to n. Now, once I know q I 0, I can compute q I 1s for all of them, all values of 1. So, what I am doing is for I equal to 1 to n, so I am finding out all first degree Lagrange interpolating polynomial, then all second degree Lagrange interpolating polynomial, and then the last nth degree interpolating polynomial. And how we are doing it? We are doing it iteratively, and we are doing it like this. So, I equal to 1 to n, and then we have got only j equal to 1 to I, because then there will be only n minus 1 first degree interpolating polynomial, n minus 2 second degree interpolating polynomial, and n minus n minus 1 will be first degree nth degree interpolating. So, there will be only one interpolating polynomial of degree n. So, we are doing it from 1 to I. So, q I j is given by x minus x I minus j. See, the data points for q I j are starting from x I minus j up to x x of I minus j up to x I, and therefore, we are taking here first factor as x minus x I minus j into q I at j minus 1 minus x minus x I into q I minus 1 and j minus 1s. So, both these polynomials are of degree j minus 1, and because they are multiplied by a linear factor, the total degree of the numerator will become jth degree polynomial. So, q I j is also jth degree polynomial. So, that is how this formula can be justified, and in the denominator it is just difference of the x I minus x I minus j, the last point, last node minus the first node value. So, that difference we are taking. So, that is just a constant. So, thus we get q I j as a jth degree polynomial, and we repeat this both these loops till they are completed, and so that will give you all the desired Lagrange polynomials. We are doing it through illustration. So, this simple illustration we are now trying to understand. So, we are saying that implementing Neville's algorithm for illustration 2, again we are continuing with the same illustration 2 which we did it in the earlier module, and we get the following tabulated results for that. So, we have got data points. What is the input to this? Data points we have to give, and the n is 3, data points are 0 0 n plus 1, 4 data points. So, 0 0 now 0.5, 0.57. So, we are saying that implementing Neville's algorithm for illustration 2 at x equal again we are continuing with the same illustration 2 which we did it in the earlier module. Output to this is going to be, and we get the following tabulated results for that. So, we have got data points. What is the input to this? Data points we have to give that point, and it will be, and the n is all the 3 data points are 0 0 n plus 1, 4 data points. We can 0 0, and that can be given as an output. So, it is given as shown in the following table. We can consider this as an output. So, I am writing this table in such a way that the computation of the q I j will be easier and quite evident from the table. So, for that what I am trying to do is first column is I. So, 0 1 2 3, then x I what are the xi nodes on that. So, first node is 0, second node is 0.5, third node is 1 and last node is 2. Then we are taking x minus xi, because we want those factors to be multiplied in the formula, and therefore, I am considering x minus xi factor. So, x minus xi we are considering first will be, because x is 0.7. So, I am writing value of x there. So, 0.7 minus 0, that is 0.7, 0.7 minus 0.5 is 0.2, 0.7 minus 1 is minus 0.3 and 0.7 minus 2 is minus 1.3. So, that is how the second column gives me the values. Then I am initializing my qi zeros. Now, you know that they are nothing but the data points. So, qi 0, so q 0 0 will be 0, q 1 0 will be 0.57, q 2 0 will be 1.46 and q 3 0 will be 5.05. So, that is how I get all 0th degree Lagrange polynomial, which are nothing but the values of yi's. Then we find real calculation starts from column 4. So, in the column 4 I want to find out qi 1. So, qi 1 how do I get? So, I will get qi 1 will be polynomial of degree 1. So, I have to go one step behind. So, that means now this polynomial I can calculate at x 1, x 2 and x 3. So, I equal to 1. So, I can get qi 1, qi 2, sorry q 1 1, q 2 1 and q 3 1. Only these 3 polynomials I can get from here. So, when I am trying to find out q 1 1, I am using data points x 0 and x 1. So, those values I will be using. So, this is calculated as I want to find out 0.792. So, what I am going to do? I am going to do the cross multiplication here. So, I am taking 0.7, that is factor x minus x 0. So, that is the first factor into last value minus last factor, that is x minus x 1 into first value there 0. And if you see that the difference. So, 0.7 into 0.57 minus 0 into 0.2, you will be getting 0.792, 798. Then in the second entry in that column, I get it by taking 2 points at 1 and 2. So, I will be getting 1.46 into 0.2. So, that is this minus 1.46 into 1.46 into 0.2 and minus 0.3 into 0.57. So, I have to multiply by minus 0.3 into 0.57 and I have to subtract. So, that will be added, and when you do that I will get 0.926. And if I take number 3, then I will be using 2 data points 2 and 3, and that is calculated as minus 1.3 into 1.46 and minus plus 0. Minus 0.3 into 5.05 minus plus 1.3 into 1.46, and that will give me 0.383 as the value. Now, when you are doing the calculation for in the next column, I am calculating all second degree interpolating polynomials. For second degree interpolating polynomials, I need 3 data points. So, I can calculate only q 2 2 and q 2 3. So, q 2 2 if I have to calculate, the first set of points will be 0 and 0.7 and last set of point will be 1 and minus 0.3. So, these 2 pairs I am going to consider, and then I have to multiply this. So, what I have to do, and I have to consider now the value x factor is this 0.7 and minus 0.3 is the last factor that I am going to consider, and the values I am going to consider are points previous value. So, first degree polynomial value I have to take. So, that is 0.798 and 0.926 I have to use. So, 0.926 into 0.7 minus 0.792 into minus 0.3, and I have to divide this by 1 minus 0. When I have divided by 1 minus 0, I will be getting 1 only. So, therefore, it will be just the difference. In the earlier case, I forgot to tell you that I have to divide by 0.5 minus 0, 1 minus 0.5 and 2 minus 1. So, I have to divide by those factors to the previous case. here we have to divide it by factor 1 0, and then for calculating the second value, that is q 3 2, I will be using values as 0.926 and 0.383, and on the in the third column I will be using 0.2 and minus 1.3. So, I will be taking 0.383 into 0.2 minus plus 1.3 into 0.926, and I have to divide it by 2 minus 0.5, that is 1.5 I have to divide, and when I do that I will be getting 0.8536. And when you are trying to calculate q 33, so third degree polynomial, there will be only one. So, that is q 33, and for q 33 my first point will be again 0.7 there and minus 1.3 last value, and I have to use 0.8876 and 0.8536. So, previous two values I have to use. So, 0.8536 into 0.7 minus plus 1.3 into 0.8876 divided by 2 minus 0, and that will give me 0.8757. So, this gives us very clearly the Lagrange interpolating polynomial. Note that you can see here q 21 gives us the estimated value of bilinear Lagrange polynomial over value by linear Lagrange polynomial over 0.5 comma 1, in that interval I am getting. q 22 and q 32 gives the estimate of value of the y 0.7 by quadratic Lagrange polynomial over 0 1 and 0.52. Okay. So, that means again I will repeat this. We are getting q 21 gives us the estimate of value of y at 0.7 by linear Lagrange polynomial over 0.5 and 1. q 22 and q 32 gives the estimate of value of y at 0.7 by quadratic Lagrange polynomial over 0 1 and 0.52 respectively, and q 33 gives us the estimated value of y 0.7 by cubic Lagrange polynomial over 0 to 2. We have seen these values we also calculated in illustration 2, but here this table gives us all the three values readily available from the table, and you do not have to do independent calculations for these values. Now, if you compute the time complexity of the Neville's algorithm, what you have to calculate is you have to calculate how many additions. We are calculating time complexity in terms of arithmetic operations that are performed in the algorithm, and we assume that suppose that any computer implementation, a specific computer implementation takes a amount units of time for doing addition or subtraction operation and m units of time for doing multiplication or division operation, and then how many such operations are performed in the during the execution of the algorithm, that will determine the time complexity of that algorithm. So, therefore, if I want to calculate time complexity for evaluating q n n, I have to go through the entire process. So, I have to go through that entire for loop which is given in the algorithm, and therefore, what will happen here is that from Neville's algorithm I am trying to find out this. So, what is the Neville's algorithm? You know that you can see here this is my Neville's algorithm. So, I am executing this for loop for I equal to 1 to n, and second for loop is j equal to 1 to I. So, therefore, each loop. So, first when I is equal to 1 I am executing is 1 time, I equal to 2 I am executing 2 times, and I equal to n I will be executing it n times. So, that means total number of for loops that I am going to evaluate, or the q I j expression is evaluated, is n into n plus 1 by 2 times. So, that is what I am writing here, that we are considering this Neville's algorithm n into n plus 1 by 2. So, n into n plus 1 is n square plus n by 2 number of times that expression for q I j equal to that is evaluated. Now, with that expression, how many product and division operations are involved? If you look at this, there will be 2 products in the numerator and 1 division I have to perform and 1 subtraction operation I have to do. So, all these operations together will take 3 m plus a times, and therefore, I get here the from Neville's algorithm we get number of operations that are performed will be 3 m plus a into n square plus n by 2 times. Directly from the Lagrange interpolating formula, if you do, now if we are working out the through Lagrange interpolating formula, then what will happen? So, how many such multiplication operations and division operations I will have to do, because in evaluating each term I will have to perform 2 m multiplications and additions. So, 2 m into 2 m plus a, total number of say we are evaluating all the Lagrange interpolating polynomials. So, 2 m plus a into n square plus n in plus n a. So, where m and a are the time required for one multiplication and one addition respectively on the specific computer, that is what I have already told you. So, this is what is required by if you are evaluating nth degree Lagrange polynomial interpolation Lagrange interpolating polynomial, then I will be requiring 2 into m plus a into n square plus n time plus n into a, because there will be number of additions we will have to do all the terms. For calculating each term I will need some time, and then for calculating the sum of all the terms I will need some time, that is n a additions I will have to do. So, asymptotic complexity if you take, then both is order n square. What do you mean by asymptotic complexity? The time complexity will depend on the size n into so n square into constant multiple. So, time will be within the constant multiple of n square, that is what we call it as a asymptotic time complexity, and therefore, for Neville's algorithm asymptotic time complexity is order n square, and for Lagrange interpolating formula also the time complexity is of order n square. So, that way asymptotic time complexity we do not get much, but there are many added advantages here. Added advantage in Neville's algorithm is that it computes estimates of y at x using all interpolating polynomials of degrees less than or equal to n, not only n polynomial. Another important advantage of Neville's algorithm is that an additional data point, if you are given, suppose you have already done the data set and then you come to know that there will be additional data point is available and you want to increase the degree of the polynomial, in the Neville's algorithm you need only to go to the next column, that is it, nothing more than that, and therefore, the time required for calculating. So, added this another advantage is like this, that if an additional data point x n plus 1 and y n plus 1 is added to the data set, then the values of new Lagrange polynomial can be computed just by evaluating q n plus 1 comma j x for j equal to 1 to 3 up to n plus 1 using values q I j x for I equal to 0 1 to 3 up to n and j. On the other hand, in the Lagrange interpolating polynomial probably we will have to do more work in that. This is another advantage here. So, Neville's algorithm is beneficial in the sense that it computes all the subsequent lower degree Lagrangian polynomial from the given data set, including the nth degree polynomial, which is our final objective, plus which is not possible in Lagrange. In Lagrange each time we will have to do the fresh calculation, and plus this another advantage that if you are adding a data set, the additional Lagrangian polynomial can be easily calculated through this. Now, as this so asymptotic time complexity we already talked about. Note that evaluating the nth degree polynomial interpolating polynomial over data points x I y I using usual basis p x. Now, I am comparing with the, if you are normally doing this computation and suppose instead of taking special forms of this polynomials, we take usual form of a polynomial and you substitute those n plus 1 conditions, then I will get a system of linear system of n plus 1 equations in n plus 1 unknowns, which is required to be solved, and if you want to do that, it will take about order n cube time complexity. So, by selecting a specific form of the interpolating polynomial, we could save a lot of time, because it is order n square, whereas the otherwise it will be order n cube, and that makes a lot of difference in the time complexity requirements. Now, we talk about interpolating error. As we know that the interpolating polynomial p x approximates the functional relationship y equal to f x between the dependent variable y and independent variable x, right, which precisely match with the observed values of y at the nodal points x 0, x 1, x n. So, I want that the relationship should be exact at these nodal points. However, at any intermediate point x, the approximate value p x differs from the exact value f x, and E x, the difference of these two values, can be considered as interpolating error at x. So, except for interpolating error, as the nodal points will be 0, because f x and p x values are same. But if you take any other point than the nodal point, then interpolating error will be non-zero, and that error we are denoting it by E x. So, E x true error will be E x equal to f x minus p x, but which can be evaluated only if exact value f x of f x is known. In general, it is not known, and therefore, in general it may not be possible to find out exact error E x. So, in many situations, the user has an idea about the exact relationship y is equal to f x, and still he wishes to approximate this f by an interpolating polynomial p x, as the form of f may be too complex, or for any other situational reasons. For many other reasons, you may need a polynomial representation. Then in such a case, it is possible to evaluate this error E x, or at least compute an upper bound on error E x over the domain of observation. So, our idea is that how much maximum error I can commit. So, that means upper bound I am trying to find out on the error using the over the domain of observations. The following mathematical facts. Now, this is a result which is well known result in mathematics and can be proved. Many books gives the proof of this result also, and we can obtain is like this, that suppose we have got x 0, x 1, x 2, x n are distinct points in A B, such that we are taking in the increasing order, just to know that what is the first point and last point A B. So, f is from A B to R is a function that we are considering, is a n plus 1 times continuously differentiable function. So, I want this to be continuously differentiable function n plus 1 times, and if p x is an interpolating polynomial approximating f over the nodes x 0, x 1, x 2, x n, then for any x belonging to A B, there exists a number z x in A B such that this is what happens. So, z x in A B such that E x equal to f x minus p x into f n plus 1 z x upon n plus 1 factorial into x minus x 0 into x minus x 1 into x minus x n. You can refer to any of the books which are given in your additional reading material file, and you can refer to this and you can get the proof of these results. If there exists a positive real number capital M, now what is happening is here unknown, see n plus 1 n is known, so n plus 1 factorial is known, the data values are known, x 0, x 1, x 2, x n is known. If x is known, you can find out the product of this factor, there is no problem about that. What is unknown is f n plus 1th derivative and the point z x, because z x is any arbitrary point we are saying, some point there exists some point in the interval of observation we are saying, which is not fixed, which is not known also, and therefore, what we do is we find the estimate. So, what we do is we try, if we can get some upper bound on the n plus 1th derivative of x on the whole interval A B, that means I am trying to find out a real number m such that mod f n plus 1 x is less than to capital M for all x belonging to A B, then most natural upper bound on E x is given by mod E x less than or equal to m upon b minus a, because x minus x x 1 x 1 both all the points x and x i's are all inside the interval a b. So, their maximum value will be b minus a, and therefore, if I replace all these factors by b minus a, I will get m into b minus a raised to n plus 1 in the numerator divided by n plus 1 factorial in the denominator. So, that will be very crude upper bound on the error. So, we may illustrate this by taking an illustration. So, let f x equal to e raised to 2 x into cos 3 x for x belonging to 0 to 1. I want to represent, I want to consider this and find the approximate value of f at 0.5 using Lagrange interpolating polynomial of degree 3 over the nodes this. So, we are given nodes x equal to 0, x equal to 0.3, 0.6 and 1. So, you have got 4 nodes and third degree Lagrange polynomial we are trying to find out, and we also want to compute the error bound over the interval whole interval 0 to 1, because the points are given in interval 0 1, and the actual error E 0.5. So, what is the actual error at 0.5? In this case, actual error we can find because form of f x is known. Now, what we are doing is we are trying to calculate it by Neville's algorithm. We are trying to find out the Lagrange interpolating polynomial by Neville's algorithm, and this is again that table explains to you that I is given as 0, 1, 2, 3, x I is 0, 0.3, 0.61, x minus x I, x is your 0.5 we are given already. So, 0.5 minus 0 is 0.5 and all that we get. Then q I 0 are the values of y I. How do you get these values of y I? We are computing using functional relationship. So, if I want to find out at x equal to 0 what is the value of y f x or y I, that will be x equal to 0 e raised to 0 will be 1, cos 0 is also 1, and therefore, the value is 1, and therefore, in this column the first entry the fourth column first entry is 1, and that is how you calculate the remaining entries by substituting specific x. Then you calculate those first degree Lagrangian polynomial, second degree Lagrange polynomial and third degree Lagrange polynomial and their value. We are not getting those polynomials, we are getting the value of these Lagrangian polynomials at that point x, that is what we are getting. We are not getting Lagrange polynomial as such. So, we get this, and this table tells me that the value is 0.13133. If you look at the graphical representation here, then original curve I know which is given in red, and the green shows me the Lagrange interpolating polynomial. You can see that it matches quite closely on some portion and does not match in some portion, but it is quite close to the original curve. So, in order to estimate the error in this particular case, what we need to find out is the exact value of f 0.5, which we already computed as 0.19228, and estimated value of p 3 0.5 is equal to 0.13133, and hence the difference is the error. So, that is E 0.5 will be equal to 0.06095. Note that the quadratic interpolation over the interval 0.31 gives the better approximation, as P 2 0.5 is 0.16358, which is closer to the exact value, and the error in this case turns out to be equal to 0.0287. One can compute the fourth derivative of x, and that is given by minus 119 e raised to 2 x into cos 3 x plus 120 into e raised to 2 x into sin 3 x, and hence an upper bound on the error. Say, since your x varies between 0 and 1, upper bound on the error will be given by something like 239 into e square by 4 factorial, and which amounts it to be equal to 73.58 for all x between them. So, this is bound on the whole interval 0 1, but you can see that the bound is very crude, as the value is 73.58, whereas our size of the error is roughly 0.06 or 0.02 and so on and so forth. So, in the summary, we can say that in this module we discussed Neville's algorithm for efficiently evaluating Lagrange interpolating polynomial. We saw the time complexity of this algorithm, interpolating error, formula for evaluating this error, and upper bound on the error. All these things we discussed in this particular module. Thank you.